Hello everyone, you are welcome to the second session. We are still in the first part of linear algebra. Here we will revise some concepts of matrix analysis. I just wanted to mention here that in order to be able to follow that my presentation, it is good that you if you have some book in matrix analysis or in linear algebra, so you can revise and you can study from them, so it is quite general. Of course, you can use also the same textbook of this course, but as you maybe observed that we cover more topics than what are in the textbook. Okay, so now let us start from where we ended the previous session, when we talked about vectors, and we differentiate what is the difference between a scalar and a vector. And we mentioned that vectors usually represent direction and magnitude, and it is represented in higher space dimensions than a scalar. So the scalar is only on the line of real numbers. But when we talk about vectors, then we talk about multidimensional space. So for example, if we have vector with 2 elements, then we talk about 2 dimension. If it is a vector with 3 elements, then it is a line, but it is in 3 dimensions. If it is like in n elements, then it will be a line in n-dimensional space. Okay, so now what are the matrices? When we talk about matrix, the matrix actually is let me just start with the pen with white color. Okay, so the matrix, which is represented, as we know that, for example, in this form. So if we have this matrix, let's say it is 5 2 0 1, then this matrix now is represent like 2 vectors, as you can see. One vector, this is vector 1, and this is the second vector, and both of them now they are representing some space. Now they are representing some space which are spanned by these two vectors. Okay, and we know that if we want to multiply this matrix with x, with vector x, for example, then we write it like this way. Okay, and this will be, for example, it is 5 2 0 1 times, let's say, x1 and x2. If you remember from the first session, the legal to make this multiplication legal, we need to have this is the number of rows. For example, here we have 2, number of rows 2, and number of columns 2, and here we have the number of rows is 2, and we have 1 column. And if you remember that the number of columns in the first matrix or vector should be the same as the number of rows in the second one. So now it is possible to generate a legal multiplication of this one, and then the result will be like 5x1 plus 2x2. Okay, this is the first element, and the second element is 0x1 is 0 and plus x2, so it will be x2. Okay, and just basic revision also. So if you have like a problem that could be represented by system of linear equations, we call this as a system of linear equations. So it can be, for example, ax equal to b, and b is the result. So actually what we are doing here is we map x with by the multiplication of a and x, we have mapped x into the space of a, and then we got this result, which is b. For example, if we keep the same numbers here, that we have 5 2 0 1 x equal to, let's say it is 1 and 2, for example. So it means that what is x, which is when it is mapped to or projected into this in space 5 0 2, 1, it will be a vector with 1 and 2. It is of course very easy to solve this one, as we know by solving system of linear equations, and this is of course 2 by 2. It means that it is square matrix. Since it is square matrix, if it is non-singular, okay, then it is possible to find the inverse of this matrix. So in general Ax equal to B if A is square matrix and A is non-singular. Of course we are going to explain these things in the coming slides, but now just for those who have already some background. So now we can have that X equal to A inverse of times P. So when we multiply the inverse of A times P, we will get that, or we will solve this X. So taking the inverse of A, it means that is that the matrix where we multiply it in A inverse, we get the identity matrix. Okay, in 2 by 2 matrix, identity matrix is actually 1 0 0 1. This is called the identity matrix. It is very similar in the scalar case. For example, if you have let's say 2x equal to 8, how to find x? You can find x by multiplying both sides by the multiplication inverse of 2, which is half. Then we can have this is half times 2x equal to half times 8, and then this will be x equal to half times 8 is equal to 4. This is in the scalar case. In matrix case we are doing the same, so we take the inverse of the matrix, but there are two main conditions for this matrix to have an inverse. That the first condition, that this matrix must be square matrix, and the second thing, that it must be non-singular matrix. Okay, there are many cases where the matrix is square and also non-singular, but also still it doesn't have inverse in weak condition. It means that you can't compute the inverse here. You can compute the inverse, but this inverse will have like very large numerical errors, and this is called ill-conditioned matrix when the condition number is very large. Of course we are going, as I said, to explain this more and more during these online sessions. Okay, if we go back to the same problem to solve this one, now it is clear that because we don't need to find the inverse of this matrix, because that if we make the multiplication and we represent this as a two equations, it will be like 5x1 plus 2 times x2 equal to what? Equal to 1. And the second equation is 0 times x1 is 0, 1 times x2 is equal to x2 equal to 2. Now we have x2 equal to 2, then we can substitute in the first equation, so we will have 5x1 plus 2 times 2 is 4, plus 4 equal to 1. Okay, as you can see it here, I don't have more space, so I will move to complete it here, for example. Then it will be like x1 equal to 1 minus 4 is equal to minus 3, minus 3 divided by 5 equal to minus 3 over 5. Okay, so this is x1. Then x, which is the solution of this system of linear equation, is x vector equal to minus 3 over 5 for x1, and for x2 is equal to 2. Okay, now when you have this vector, okay, mapped or projected in this space A, the result will be a line as minus 3 divided by 5 and 2. This will be the new line. Okay, so let me go to the next slide. or to free slide to continue. Yeah. Yes. So now in the beginning that we had x. So we had x equal to, as we said, that 1 and 2. Sorry, it was minus 3 over 5 and 2, and we have b that it was equal to 1 and 2, if I remember well. So the idea here is that when we multiply matrix A times x, it will generate this p. So now if you look to this x was minus 3 over 5, minus 3 over 5, it is somewhere here, okay, minus 3 over 5 in x, and in y it is 2, if this is x and small x and y, okay, and then in y axis it is 2, so now this is the vector, represented by x bold. Usually we represent vectors and matrices by bolding the letter. So it is now, this is x bold, okay. Now when we multiply this x by matrix A, what matrix A will do? Matrix A usually it can rotate the vector x, and also it can scale. So it can scale and rotate the vector x toward vector B, and now the resultant, for example, it was 1, 2, it means that it is 1 in x basis. Now we have two basis function, orthogonal basis function, as explained in the first session. So it was 1 and 2 in y, it will be like this, so it is the same 2 here. So it will be now the resultant, it will be this one, this is B vector. So by multiplying A by x, we rotate this original vector x toward this vector B. So remember in general that projection of any vector x in any space or any matrix A, the impact of matrix A on x, it will be rotation and scaling. Rotation and scaling. It means that we change the phase and it change the scale or the length, because in general vectors, as we said, it consists of two things: magnitude, which is the length, and also phase theta, which is the angle. So we have, for any vector, we have magnitude and phase theta, and then by multiplying x into matrix A, actually it will be like rotated and also scaled to another vector. So this is in general way. Now let us go a little bit more deeper to understand what we are doing now. Okay. Let me assume that we have a matrix that it is, for example, 1, maybe 2, 3. Okay, we do something else here, maybe 1, minus 1, 0, 2. What this mean? Now we have two vectors. We can maybe call them like vector 1 and vector 2. Okay, and those vectors are three-dimensional. So v1 and v2 belongs to R3. So it has a three-dimensional space. Okay, now in this three-dimensional space we have two lines. Line represents vector 1 and line represents vector 2. Okay, and in these two vectors, what is between them is we call them as a plane, as we are going now to explain. Assume now that we want to multiply. This is, of course, the dimension is 3 rows times 2 vectors. Okay, and now we have like x1, x2 as before, and this will be, as you can see, that it is 2 rows times 1 vector. So those are the same, and the result will be 3 by 1. So the result will be like b1, b2, and b3. Okay, so this is the resultant vector by this multiplication. Okay, this is the way. Actually, if in basic linear algebra, usually they solve such kind of equations like simply by making this row multiplication. You multiply row by vector, by column, and row by column. So the result simply will be x1 minus x2 equal to b1, and 2x1 minus 0x2, it will be minus 0, it will be b2, and the third equation is 3x1 plus 2x2, the result is p3. This is the way that we know to represent this matrix multiplication or system of linear equations into this form, expanded form. This is called usually compact form, because this we can call this is a times x equal to b. So this is the compact form of this representation. Okay, and this is what we can we may have in practical. So in practical, we might have system of linear equations, and we need to solve them in order to find or to address the values of x1 and x2, and this of course can represent infinity number or countless number of real problems. So we have many problems in physics or in business, in finance, in engineering. We have too many problems that it can be represented as system of linear equations. Okay, now you know that the interesting thing that the same equation, it can be represented completely in different way. The same equations, you can see here we have x1, 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 and here we have x2, and of course 0 times x2 and x2. So this is also 0 times x2 actually. Okay, what we can do here, the same equation, both of them, we can represent them in completely different format. That we take the first vector 1, 2, 3 times x1 plus the second vector minus 1, 0, 2 times x2. Okay, and this will be b1, b2, b3. Actually, maybe it is not that common to use this representation, but it is completely correct, 100% correct representation of the same problem. You can take the first vector, you multiply it by the first element, the second vector multiplied by the second element, and it will be the same result. Of course, if you have like three columns and you have 3x, it will be also the same. This is very general. It can be expanded in any system of linear equations. Okay, what is hidden here? What is the new thing that we can see from this representation? From this representation, actually, it gives us more insight about the system of linear equations, because it tells us that simply any resultant will be like weighted sum of the columns of the matrix A. Because what we did here, just we multiply the first vector from the matrix A, the first column, by x1. x1 here is a scalar. Remember, this is x bold is a vector, but x1 is a scalar and x2 is a scalar. So we multiply the first column by a scalar plus the second column by another scalar. Okay, what that mean? It means that x1 is a scaling factor, is just a scaling, but it will not change the direction of the first column. And also the second x is another scalar, and it will not also change the direction of the second column. It will change only the scale. It will change only the length of this vector, but it will not affect the face. Okay, so what that mean? What is the concept of that? Actually, it has very important like concepts here. The first thing that by changing any x1 and x2, for example, for any x1 belongs to real numbers R, and also x1 and x2 belongs to real numbers R. Actually, by changing both of them, okay, you will be able to have many values of b1 and b2 and b3. Okay, and those values, it will be a plane like limited or certain shape a plane inside the 3D, but it will not cover the whole plane. It will not cover the whole plane. It will be just part of that plane. It will be like filled by changing x1 and x2. So by changing x1 and x2, we can generate different vectors b1, b2, b3 inside that plane. Okay. Let us go to the another slide, a new slide, to have more space. Okay. So now if we are in 3 space, like this one, x, y, and z, or and z, and now by those 3, we have now 2 elements, which was represented by vector 1. Assume that this is vector 1 and this is vector 2. Okay, now all the projection of this vector 1 times x1 plus vector 2 times x2, it will generate b. So if you take, for example, certain x1 and 2, let's say we start with x1 equal to 0 and x2 equal to 0. In this case, we will have the vector b equal to 0, 0, 0. Okay, so always the origin vector will be part of this multiplication. So we have here point in the origin. Okay, now if we have, let's say v2 equal to x2 equal to 0, okay, and we have only x1 equal to 1, then we will have the original vector. Okay, now if you put x2 equal to 2, x1 equal to 2 and x2 equal to still 0, what happened now? Actually, you will have the same vector x1, but it will be extended. So it will be extended to the double. Okay, it will be only the length will be added, and so on. So you can have actually like infinity length of this, because x1 can be up to infinity, so you have infinity length of x1. The same can be done if we put x1 equal to 0 and we just change x2. So actually we are moving here, we are moving on the line of v2. This is v1 and this is v2. Okay, now what happened if you put like x1 equal to 0.5 and x2 equal to 0.5? Actually, what happened here? We will have a new vector, which is v1 plus v2 divided by 2. So it will be something in between. It will be some line in between as an average of these two vectors. Assume that it is somewhere here. Okay, now you can take any numbers. So actually, you will have many lines. It can be projected in between here. So at the end, if you use infinity number of possibilities, you will have some certain plane with all possible points. However, remember, because the vector here is in the 3 dimension, but we have only 2 vectors, because now we have as we said, that is 1, 2, 3 times x1 plus, okay, minus 1, 0, 2 times x2. Okay, now you can have any elements here, but there are some places that it is not possible to have it. Okay, I give you one example. Is it possible to generate this number? For example, let's say it is if we assume that x1 equal to 1 and x2 equal to 1, then 1 minus 1 is 0. Okay, and 3 plus 2 is 5. Okay, here it should be what? Because x1 and x2 equal to 1, so this one should be like 2, because 2 times 1 is 2. But I will not put 2, I put like 10. Okay, I will put 10. So now if you want to find is it possible to have this configuration or not? Okay, what it means that I need to find x1 minus x2 equal to 0 and 2x1 equal to 10, sorry, and 3x1 plus 2x2 equal to 5. Okay, from this equation we know that x1 now equal to x1 equal to x2 from this equation. Okay, if you substitute it here, then you will get x1 equal to x2. It will be like 3 times 2x1. It will be 5x1, as actually we assumed at the beginning. So x1 should be 1. Since x1 equal to 1, x2 equal to 1, but here it will not follow the same concept because 2x1 is equal to 10. What it means? It means that the point 0, 10, 5 is not part in this plane. So it is not part in this plane. It is not possible to generate this number. This b cannot be possible to be generated how in any value you change between x1 and x2. For this example, it is not possible to generate this b. This 0, 10, 5 is outside the plane of this configuration. So it is somewhere, for example, here, is not here inside the plane. Okay, so this is important to remember, that not every point can be mapped. Not every point can be mapped by this linear operation. By this linear operation, that it is only finite number, or we will have finite, not finite number, but finite space actually in the 3D space. Okay, good. Now let us go further with the another point. Remember, now we are not, I said that before, but I repeat it. We are not giving a complete course in linear algebra. I am just picking up some important topics that we will be used later. So I am trying to just remind you with those important parts here. For example, many students studied already linear algebra, but they didn't catch the concept of spaces and bases. So that's what we are trying now to explain them with some numerical analysis. Okay, we go now to the next slide. Okay, well, now we was talking about this matrix A with the elements, as we said, 1, -1, 2, 0, and 3, 2. Okay, now let me add another vector. This is vector 1, vector 2, and let me add another vector here, and I will add, for example, 0, 2, and 5. So this is vector 3. Okay, now with this vector, or this matrix, sorry, with this matrix, now we have a 3 by 3 matrix. So how does this vector add a new space for this basis function or basis vectors or not? Actually not. Why? You can see here vector v3 is just the addition of those two vectors. So 1 minus 1 is 0, 2 plus 0 is 2, 3 plus 2 is 5. So actually v3 is nothing but v1 plus v2, which means that in the previous slide, when we talk about the space spanned by these two vectors v1 and v2, this is v1 and v2. Okay, the space, the plane here, actually v3 is only just a point inside that plane. So v3, remember, v3 here is not independent. v3 is not independent of v1 and v2. v3 does not add any new information for these coordinates. It is just a linear combination between v1 and v2. I repeat, any vector vi generated by the addition of any two numbers, I will call them alpha and beta, not x1 and x2, to make it more general. So alpha v1, okay, plus beta v2, for all alpha and beta belongs to the real numbers R, then this vi is just a linear combination of v1 and v2. It will not add any space, it will not add any new information, just a combination of both vectors that we have already. So it is like redundancy that we have here. So it is based on the same, on the two vectors that are already represent the columns of this matrix. Okay. Now we can call what are the linear combination or linear dependent. The linearly dependent vectors in general. So if you have any vector v1 and any vector v2, if you can find any alpha or beta such that alpha v1 plus beta v2 equal to 0 vector. 0 vector means that vector with all zeros element. Okay, for any alpha and beta belongs to the real numbers are except 0. So alpha does not equal to 0 and beta does not equal to 0. So, but because of course if alpha and beta equal to 0, the result will be 0. There is no question about that. But if alpha and beta belongs to R and both of them they are not equal to 0, those two scalars alpha and beta, however still you can find this alpha and beta and makes the summation equal to 0, then we call here v1 and v2 are linearly dependent. They are linearly dependent. In general, for any number of vectors, for example, if you have, let's say, 5 vectors, then in general, alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 plus alpha 5 v5. If you can find any alphas that from alpha 1 to alpha 5 that are not zeros and belongs to R for any real numbers to make them 0, then we have those, they have linearly dependence in these 5 vectors. The linearly dependent can be between any of them, at least one of them will be linearly a combination of the others, at least one of them. Maybe we have 4 independent and 1 linearly dependent, so that you can fix it in a way to have zeros without need to put all of them equal to 0. So this is actually one of the most important concepts in linear algebra, especially when we apply them in deep learning and in machine learning. So linearly independent is important to formulate any matrix A. Okay, because now actually you can add any number of columns which are like just combination of the first 2 elements, as we can see in the next slide. Okay, if we go to the next slide. Yeah, so now you can, for example, as we said, this is our original matrix A. It is 1, -1, 2, 0 and 3, 5. Actually, those 2 vectors, they are linearly independent. Here, linearly independent doesn't mean that they are orthogonal, because actually you can also calculate the phase between them. Okay, you can compute the phase between them, and this we can do it by the dot product, as we can see maybe later if I remember to do it now. But let me check that if this is v1 and this is v2, now you can, as I said, that if we add 0 to 5, as I said, that v3 is just a linear combination of those 2, and if you add v4, so you can, maybe we can see that 2 times v1 minus v2. So this is 2 minus is a plus, so it will be 3, and 2 times 2 is 4. 4 plus 0 is 4. Okay, and 2 times 3 is 6. 6 plus 5 is 11. So now we have 4 vectors. Still, we have only 2 independent vectors. Those 2 are just linearly combination. Actually, remember, you can add infinity number of linear combinations of this matrix A, but all of them, they will be nothing more than a points in the space formulated by these 2 vectors. Okay, so all the others are just redundant, are just combination of these 2 vectors. It will not add any new information to this matrix. Okay, and in that case, we have a new term here, is the rank. So the rank of matrix is the number of independent columns in any matrix. So now, even if you have infinity number here, okay, in this matrix, for example, even if we have a 3 times infinity, okay, so we have 3 rows but infinity column, but only 2 columns are independent, then we say that this is matrix A. We say that the rank of A equal to 2, regardless of the number of columns here, as far as all of them, they will be just a different linear combinations of these 2 vectors. Okay, it doesn't have any new information. It will not add any new information. This is important, very important in machine learning and in deep learning engineering. Okay. Yeah, before I continue, as I promised to show you how to compute the phase between any 2 vectors. For example, I have vector 1 v1 is equal to 1, 2, 3, and vector 2 v2 is equal to -1, 0, 5. As I said, now both vectors are independent to each other. However, there is some phase. It can be phase, it can be orthogonal or non-orthogonal. We can compute the phase simply by the dot product. So the dot product, that if you multiply, as you can see, that this is 3 times 1, and this is also 3 times 1. So if we take, for example, v1 transpose times v2, this will be 1, 2, 3, okay, times -5, 0, 5, -1, 0, 5, and the result will be -1 plus 2 times 0 is 0, times 3 times 5 is 15, so the result will be 14. Okay, this is the dot product. The same dot product, actually, there is another form of the dot product that you can take the magnitude of v1 times the magnitude of v2 times cosine the angle between them. Okay, so now we can compute the angle. So we have the magnitude of v1. The magnitude of v1 is square root of 1 plus 4 plus 3 squared is 9. Okay, so it is 14 times square root of the second value is 1 plus 25 is 26 times cosine theta. This equal to 14. It means that cosine theta equal to 14 divided by square root of 14 times square root of 26. Now, by solving this one, you can find the value of theta as the cosine inverse of this value, and then you can find the angle between v1 and v2. Okay, this is what I promised to show to you. Okay, now let me extend this concept of vector space here. Okay, we go to the next slide. Okay, now we said that we have this matrix A. Okay, we have this matrix A, and we said that this matrix A can be actually any dimension. It can be like m row times n column, so it is quite general. Okay, and actually any matrix A could be factorized as C times R. Okay, what is C and what is R? This factorization actually is not very like standard. This kind of it is a column basis times row basis. This factorization is not very standard, and it doesn't have that many application, but it helps to understand the concepts of basis in any matrix. Actually, I think this CR factorization was maybe invented or at least proposed by Gilbert Strang in MIT. So they said here that the matrix C is the matrix which consists of the vectors of independent vectors inside that matrix. Okay, without going into many or deep theoretical analysis, let us do it with the numbers. So if I keep the same matrix as I start with, so it is 1 minus 1 0 2 0 2, and 3, 2, 5. This is the matrix that we saw. So this matrix now is a 3 by 3 matrix, but as I said, now it has only two independent vectors, v1 and v2, and this is a linear combination. Okay, of course, by the way, you can take this v1 and v3 as independent, and v2 is a linear combination, so you are free actually to mix between those, but still the rank is 2. The rank of the matrix A is equal to 2, and 2 is the number of independent columns in the matrix A. The number of independent columns in the number A, or in the matrix A. Okay. By looking to the matrix C, I will open this one and I will check which ones are independent. So I can start with the, for example, you can start from this one and you can start from this one. You are free. You can start from this one and go to the right and to the left, so you are completely free in selection. Okay, it doesn't matter. So now I will start with v1. So in v1 I have 1, 2, 3. Okay, for sure that the first one is independent now, because this is the first one, so it will be independent. Okay, because nothing more. Now I search, I look to v2. By looking to v2, actually v2 is independent, because it is not possible to find alpha times v1 plus beta times v2 and the result is 0 unless alpha and beta, both of them are zeros. And that's mean that the second is also independent, -1, 0, 2. Okay, now by looking to this one, I found that this one is a linear combination of those two, so I stop here. Okay, now this is the matrix C. Okay, now I can multiply this matrix C with another matrix R, okay, which the result will be the same as A. So the result should be as A, which is 1, -1, 0, 2, 0, 2, 3, 2, 5. Okay, so now what is the dimension of matrix R? So now this is 3 by 3. This is 3 by 2. So it is clear that, it is very clear that R must be 2 by 3, because now to make this multiplication legal, so it is 2, 2, okay, and the result will be 3 by 3. So now I know the dimension of R, how it should be. Okay, how to calculate R? The calculation of R is also extremely easy actually, because we know that the first two columns are the same as the first two columns in C. So both here, the first two columns, this column and this column, is the same as the first column and the second column in the matrix A, which means that the first two elements in the matrix R must be the identity 1, 0, 0, 1. Okay, if you like to check, it is easy to check. Okay, now it is 1 times 1 is 1. Okay, and then a plus -1 times 0 is 0, so the result will be 1. So this is 1. Okay, now I multiply the second. 1 times 0 is 0. -1 times 1 is -1. So this is the second element. Okay, now let me left this one away. This one, leave it now. Okay, and for the second element, 2 times 1 is 2, times 0 is 2. 2 times 0 is 0. 0 times 1 is 0. This is the element. 3 times 1 is 3. Okay, and plus 2 times 0 is 3. Then the last one is 3 times 0 is 0, plus 2 times 1 is 2. So this is the second. So now we achieved the first two column. What is the third column? As I said, the third column is actually the combination of, or the direct summation of the first one and the second one. So it means that the third column is alpha equal to 1 and beta equal to 1, and this is what I should put here, 1, 1. And you can check if you like. So 1 times 1 is 1, -1 times 1 is -1, so 1 minus 1 is 0. 2 times 1 is 2. 2 plus 0 times 1 is 2, because the 0 times 1 is 0. And 3 times 1 is 3. and plus 2 is 5. So this is the second element. So now the third column should be alpha and beta, so it is 1 1. Okay, you can see one thing here. What is the number? You can see that both rows are also independent. Those both rows, they are independent. You will not be able to find if I call this vector, let's say maybe u1, and this vector is u2, there is no alpha and beta, where alpha times u1 plus beta times u2 equal to 0, unless that alpha and beta both are zeros. Otherwise it is not possible. Otherwise it's not possible to have this one. So actually the number of rows, they are also independent. What is the concept here? The concept here, we come to the very important conclusion that the rank of any matrix A is the number of independent columns, and also it is the same as the number of independent rows in that matrix. I repeat it. Okay, the number, so the rank of any matrix A is the number of independent columns, and it is the same, identical with the number of independent rows. Okay, so this is actually very important rule in linear algebra. So the rank of matrix is the number of independent rows and independent columns. Okay, now assume that we have, what is the meaning of full rank? Okay, let me check one thing before I go to the complete rank or full rank. If you have a matrix A with a dimension of m times n, okay, so the rank of A is less than or equal to the minimum of m and n. For example, if you have a matrix A with a dimension of 5 rows and 3 columns, okay, so the rank of A, it will never be more than 3. Okay, so the rank of A, regardless of the content, what is the content of A, the rank of A is less than or equal to 3 in this case. Okay, so if we have 3 independent columns, then the rank of A will be 3. If there are some linear combination, then we will have like less than 3, for example 2, okay, or even 1. Yeah, I show you now matrix which is like 5 by 4, but the rank is or 5 by 3, but the rank is 1. I can show you this matrix. Okay, 1 2 3 4 5, because it is 5 by 3. Okay, and this one is 2 2 2 2 2, and this one is 3 3 3 3 3. Okay, now this matrix is 5 by 3, the dimension, but actually the second column is just 2 times the first column, and the third column is just 3 times the first column. So simply the rank here is equal to 1. We have only one independent vector, because if we call this is v1, so v1 minus 2 half times v2, the result is 0. Okay, so v1 minus half times v2, the result is 0. And of course the same for the third column. So the rank here of this matrix equal to 1. The rank of this matrix is equal to 1. So the other two vectors does not add any kind of information to this one. And also, if you look to the row space, not the column space, look to the row space. So we have 1 2 3 1 2 3 1 2 3, so just repeated. So the rank also in the from the row space is equal to 1, and this is like a theory that the number of the rank is the same for from the perspective of column space or the row space. Okay, so this is important to remember. Now, and the final point that I wanted to mention in this fast review is about the full rank matrix. Sorry. Okay, the full rank matrix. The full rank is that first the matrix is a square matrix, so it can be, we can call it like matrix A with a dimension of m by m or n by n, whatever you like. So it is, for example, n by n. Okay, and then if all the n columns or n rows, they are all of them, they are independent of each other, then the rank of A is equal to n, and in that case we call this matrix A as a full rank matrix. Okay, now if we have full rank matrix A multiplied by a vector B, and this will generate like another vector B, and as we show in the previous explanation, that we have column vector 1 times x1 plus x1 here is just a scalar, plus v2 times x2 plus v3 times x3 until vn, this is the dimension, times xn. This will be the result of P. Okay, now B is again is just a combination, a linear combination of all column like vectors. The linear combination of all column vectors which are represent, or we call them the column space of the matrix A. So just linear combination of those numbers. However, the difference between the full rank and the previous one, now actually we will have the whole space. For example, if A, the dimension is 3 by 3 and it is full rank, by making this multiplication, by changing x1 and x2 and x3 to any element, then we can have the full three-dimensional space. We can have any point here. It could be like a projection of this x times A, or the rotation or the mapping of x in the space of A. And the reason is that because actually x now is just the inverse of A, because A is square matrix and it is full rank, which means that it is non-singular matrix, so it has inverse when we multiply it by B. So by generating any B point here, you can multiply it by A inverse, and then you can see how it will be on the X space or on the X vector. What is the X vector that it can generate B vector? So it is possible to, it is connected now. B and X, they are connected always by this matrix, the A inverse. Okay, so this is just introduction and about what I want you to remember from this fast presentation or fast review. That remember the concept of column space and row space, and the rank of matrix, and the mapping that when we multiply two one vector in a matrix, actually the impact of the matrix will be a rotation and scaling of this vector x toward another vector which is B, and this rotation as well as scaling is nothing but a weighting combination of the vector space of the matrix A. So this is the important message that I wanted to say in this lecture, and then we will go to even more interesting and more deeper analysis when we talk about like the singular value, what is the meaning of singular value, and what is the meaning of singular vector, and how to connect those to the column space, and we will talk about singular value decomposition. They are very interesting and very rich, actually, a source of information and knowledge in linear algebra that it can be used. It can give us more solid understanding of deep learning and machine learning in general. Thank you very much, and see you in the next lecture.